Welcome to the Henry AI Labs walkthrough of Keras Code Examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun, generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. As a quick preface to the video, here's what you will learn from this video. You'll learn how to download a dataset from a link using shell commands in a Collab notebook. This dataset will now be on the disk, and we have to pipeline it from the disk into the working directory to pass it to a Keras model. You'll learn how to do this with the image dataset from directory Keras function. We'll see how to visualize data, and then importantly, we'll see how to define a preprocessing and normalization pipeline, where you have two options to either preprocess the data on the CPU or define it as a part of the model where this happens on the GPU. Then you'll see how to build a model, particularly the exception architecture using skip connections, and how to visualize the model using plot model. Then we'll train the model, explaining the epoch step through, and then we'll show you how to do inference on a single image of a cat and have it classify it as a cat rather than a dog. The first example is image classification from scratch. This example is going to show you how to take a dataset of images stored as JPEG files on the disk and load it into Keras to train an image classification model. In this case, we're demonstrating this using the Kaggle cats versus dogs binary classification dataset. This just means assigning a 1 for a cat and a 0 for a dog. The tutorial also describes how we're not doing this with pre-trained weights or a pre-made Keras application model. Later on, we'll describe more what this means. This references using transfer learning, where you take, say, a ResNet 18, ResNet 50, MobileNet, one of these pre-trained convolutional neural networks, and then using that to initialize the parameters of your neural network for some downstream task. And generally, that works much better particularly for small data sets. But in this case, it's showing you how to do image classification from scratch. From scratch, referencing a random initialization of this deep neural network. So we're going to use the image dataset from directory utility from Keras in order to show you how to pipeline this Keras image preprocessing, where you take the images, the JPEG files, and then you preprocess them and prepare them to get them into the working directory of batching them and preparing training loss updates for deep neural networks. We'll also look at some image standardization and data augmentation in this pre-processing pipeline. So the first lines of code are import TensorFlow as TF, from TensorFlow import Keras, from TensorFlow.Keras import layers. This is the last time in this code series that I'm going to explain these kinds of imports. Basically, all you're doing is you import the TensorFlow Python library and then you alias it with TF. What this means is that when we're going to be calling functions that are written in the TensorFlow software package, we're going to use tf dot and then access the attributes or the functions of the TensorFlow library. Similarly, Keras is a library on top of TensorFlow, and we also do from TensorFlow.Keras import layers. So this syntax from import layers compared to import as tf just means that we'll be doing layers.dense or something like that. For example, if we wanted to have the same kind of syntax, we'd do import layers as L or something like that. But this is the standard syntax of how people import TensorFlow, Keras, and the layer. So this is the last time in the Keras code series that we'll explain these basic imports. More interestingly, now let's download the dataset. So this syntax where you use the exclamation mark, this lets you use the terminal commands in the Google Colab Jupyter Notebook. So you do something like exclamation mark ls to list the contents of the current working directory. In this case, we're using the exclamation mark curl to download this file from the internet. So we hit run on this code and it runs the shell command to download this dataset. So as described, this is a 786 megabyte dataset of these JPEG images of cats and dogs that we're going to be training our image classifier. So this isn't a very big dataset. We see that Collab is able to access the dataset in about 7 seconds. This probably depends on my internet speed as well, and this may vary for how long it takes for you. But overall, downloading 786 megabytes of data across the internet, it usually isn't that much of a bottleneck. So if you go into the Jupyter Notebook interface, you now click on this folder icon and you can see the new file that we've just downloaded. So this has now appeared in our directory because we just downloaded it with this curl shell command. So now what we do is we have this zip file and we're going to unzip it so that we can get the uncompressed JPEG files. And we see now we have this pet images folder that we have our cats and our dogs. And if you like, you can click here and you could download this onto your local machine if you want. You could go into the cat folder and you could find an individual cat image and download it. So we also have a quick browser interface in our collab directory if we want to view these images. So for example, we click on 10.jpg and then we view this cat image on this side shell of our collab interface from Google Colab. So now we'll exit out this folder thing and go back to our original notebook. So we can also have the shell command ls pet images. This is listing the directories of that pet images folder, and we have two folders, cat and dog. So the next line of code is about filtering out corrupted images. So the idea of this is that we're scraping this data set from this web link. We have this https download.microsoft.com download, and some of these images are corrupted and they're not formed as JPEG images. So we want to filter out the badly encoded images by looping through this and particularly looking through the as bytes embedding. So this is a bit more advanced than our high-level overview of Keras and TensorFlow is concerned. But overall, what this is doing is it's just a way of filtering out bad files from this web scrape. So some of the lines of code, you import the OS library, use this number skip so that we have a sense of how many of these images have been corrupted. We do the syntax of for folder name in cat dog, meaning just cat dog. This is the for loop. We use the folder path as os.path.join. os.path.join basically just concatenates pet images with cat. So it'd be pet images /cat and then pet images /dog. So now what we do is for file name and os.list directory folder path, we pass in the folder path pet images /cat, and then we loop through each file name in that folder. We join the path so that we can open this file, and then we check what kind of encoding it's been. So if it's been encoded with this JFIF encoding, then we're going to increase our number of skipped, and we're going to remove it from the file path. So os.remove, that's going to delete a file. So you have this OS, this is your Python interface to your operating system, and you can use commands like os.remove or os.listdir to traverse the directory and make actions on the files. So now we're diving into the first functionality of the Keras library. This is the tensorflow.keras.preprocessing.image dataset from directory. Image dataset from directory is one strategy of loading datasets that are stored in the local directory on the disk into our current workspace to load it into our deep neural network or just any kind of training, whether we just want to plot the images or do any kind of normalization statistics. Anything we want to do with our dataset, we can use the image dataset from directory function to access it from this disk. So some of the things we do, we pass in the image size. This means the height by width. We have 180 pixels by 180 pixels. We're going to be passing in batches of 32 images to train our deep neural network. We're going to access the data from directory. This is the name of the folder, pet images. The validation split, we're going to hold out a subset of our data so that we can validate our hyperparameters and evaluate our model performance. And then we seed this so that we can reproduce the same results every time. So there might be, there's randomness with respect to how it's going to split the data. You pass in a seed such that you know that you're working with the same sets of data every time you run experiments. So this is really important for once you get into research or you're just overall trying to see what works and what doesn't. Make sure that you seed it so that the results of your algorithms that you're testing are actually due to the new algorithms, not because you've had a random different split of the data. And that's really conflating the results that you're seeing with your experiments. So we also pass in the image size argument and the batch size argument. And then we similarly do the same kind of syntax for our validation set. Our next block of code is about visualizing the data with the matplotlib.pyplot library. So what we're doing in this line of code is we define our figure, plt.figure, we define the size of the figures, 10 by 10, and then for images labels in trainds.take1. So trainds is the name of this object that is storing the parameters of our tf.keras.preprocessing.image dataset from directory. So .take is how you sample the next image. So we do for images labels in trainds.take. Each time you ask it to .take and then 1, it'll return to you another image from the pipeline of going from disk into the current Python workspace. So now we're looping through a set of 9 images, and we're going to define the plt.subplot. So this is the syntax for taking matplotlib and not just plotting one image, but plotting this 3x3 grid of the images. Then we have this plt.imageShow. The images, you convert it into NumPy. So we take this image, and then first we have to convert it into a NumPy array. So it might be loading it from the disk just as a JPEG file, or maybe it's a PIL image. I don't know exactly what it is before it gets passed into this NumPy, but we do .numpy to chain it into NumPy. You could also convert any kind of tensor into NumPy like this, and then this is how you input it to matplotlib. So matplotlib takes in NumPy arrays and plots them with this IamShow syntax. So overall, we get this nice visualization. A great way to start our models is to get a sense of what our data looks like, particularly when working with computer vision and images. Now we'll get into one of my favorite topics in deep learning, which is data augmentation. Image data augmentation are these transformations we make to the images that preserve the semantic label. So for example, we can rotate this dog image 10 degrees as shown in this random rotation hyperparameter 0.1, or we can horizontally flip it and it's still a dog. There's no way to rotate the dog or horizontally flip it such that it becomes a cat. So this is the syntax for defining our data augmentation pipeline in Keras. So we do Keras as sequential, then we have layers.experimental.preprocessing dot, and then we have the set of implemented data augmentations in the Keras library. So you can consult the Keras, you go to the Keras documentation, you go to preprocessing, and you can see all the different data augmentations that you can use right off the shelf to augment these images and then get more juice out of smaller data sets, and also to other things that data augmentation has been applied to, like training GANs with limited data or contrastive learning, to name a couple other examples. So in this case, we define random flipping and random rotations, and then we use this and then we can pass it into this batch. Remember that trainds.take is the TensorFlow Keras syntax for sampling the next image from our data loader. If you're familiar with PyTorch, you know that syntax of data loaders. This is the same kind of idea, trainds.take1. So what we do is we take each of these images and we're going to pass it through this sequence of data augmentations, and now we can get a look at what this image looks like. So we see these cats rotated and horizontally flipped. In this case, you see an example of this one, and then this one is an example of a horizontally flipped image. The next step after applying data augmentation is to standardize the data. So as it is, these RGB pixels are in the 0 to 255 range, and this isn't good for neural networks. What we want to do is standardize these values into the 0-1 interval by using the rescaling layer. So the tutorial describes two different options to preprocess the data. So there are two different ways of doing this in Keras. So option one is to make it a part of the model. So what this means is we have our data augmentation layer. We first have our inputs layer where we have Keras.input shape equals input shape. This is where the 180 by 180 RGB cat or dog image would be inputted. Then it would go through a data augmentation layer and then would go through a rescaling layer. Now the other option is to do this before you even define your model. So the other way is to take your trained data set and apply this .map syntax. You define this lambda function, which is a quick shorthand of saying take x and then y, which is the label, and then return the data augmentation transformation of x and then label this training equals true. This is something to do with the way that it's batching up the asynchronous and non-blocking batching under the hood. This training equals true. Don't worry about this particular part of this for now. All that you need to understand for now is that there are two different approaches to doing this. You can either apply the preprocessing as a layer in your model, or you can do this offline and then define your model. So you're passing in data that's already been rescaled and augmented to your model compared to implementing it as a part of the model. Okay, so hopefully this made it pretty clear. There are two options of doing this, and really the difference is going to be more at scale. It's going to be, there are papers that look at things like how you're exactly batching and then what happens on the CPU, what gets moved to the GPU with respect to preprocessing data. But for our sake of this cat versus dog thing, this isn't going to make much of a difference. But if you are doing this at large scale experiments, you should be more mindful of how this is, what's getting preprocessed on the CPU, and then how this data gets moved from CPU to GPU and all that kind of stuff. But that's going to be a little out of the scope of this current tutorial. So the next step is this prefetched, buffered prefetching. So again, this is more of the technical under the hood of exactly how data goes from the disk into our working memory space for the sake of training these models. So I wouldn't worry about this too much depending on what level you're at. If you're dealing with really massive data sets though, I would definitely pay more attention to this compared to if you're just starting out with image classification. So now we'll get into the start of the show, which is building the model, building a deep neural network with the Keras library. So we're going to build a small version of the exception network. So this is one of these, you can read one of these research papers that tells you exactly what it is about the model architecture in the exception network, but hopefully it'll be clear enough from this code that you won't need to actually consult the paper. So quickly also in the beginning, they motivate using Keras Tuner. Keras Tuner is a strategy for optimizing the hyperparameters. So to jump ahead a little bit, we see how we have these hyperparameters. For example, when we have a two-dimensional convolutional layer, this 32 feature planes could be an example of one hyperparameter. Same thing with 64 feature planes, as well as this loop through different 128, 256. These are all configurations of the hyperparameters of a neural network. So the article begins by motivating Keras Tuner as a way, once you're a little more advanced and you understand this code, and you want to start finding the optimal configuration of these parameters for your deep neural network. So as we mentioned previously, with the two options of doing normalizing the data, this is taking option 1. So in option 1, we have these two different layers and we make it all a part of the model so that we can just get the raw images, and then the model object will process the entire data. So we have the input layer, Keras.input shape equals input shape, which is the 180 by 180. Then we have that data augmentation block, which we defined up here, this sequential processing of random flipping and then random rotation. And then we have a Keras.layers.experimental.preprocessing, the rescaling layer that's going to normalize every pixel value to lie on the interval between 0 and 1. So now we start to define our convolutional neural network. So some of the key ideas here is making sure that your feature maps haven't run out of bounds or out of space, so to say. So this isn't really going to matter too much with 180 by 180 images, but say you're playing with the CFAR10 dataset where you have 32 by 32. If you use 3 by 3 convolutions with stride length of 2, you're going to decrease the spatial resolution of the feature map. So it might go from 32 by 32 to 28 by 28 and so on. And if you just stack these layers together with no sense of what you're doing, you might eventually have like a 0 by 0 thing, and it'll obviously throw an error and the whole thing will break. So be mindful of this strides equals 2. This is downsampling the spatial resolution of the feature maps, and you don't want to run out of the height by width of the feature maps. So what we do here is we define padding. This is padding. You add zeros to keep it as the same dimension to preserve this spatial resolution. You have this Keras syntax of taking the previous layer's output and then passing it in through x equals, and then you have this chaining where you add the in parentheses x, and you do this on and on. You stack these blocks together. This is the way that we define these convolutional networks. Most neural networks are just done by repeating these blocks over and over again. Like even the transformer neural network is done by stacking these self-attention blocks on top of each other, say 8 to 12 times. So the way this exception model architecture works is we begin by taking the input and passing it through 2 blocks of convolution, batch norm, and ReLU activation. Now we're going to use a residual skip connection. So ResNet's this residual connection, what it does is it projects the feature maps at say layer L-1 up to layer L+1. So that the bottleneck of going from L-1 to L+1 is alleviated by having the skip connection ahead, and it helps with preserving information flow in deep neural networks. So if you're interested in that, I recommend checking out the ResNet paper, one of the most influential papers in deep learning. So another thing to note is the syntax of looping through and constructing the neural network through a for loop. So we're seeing this, remember the syntax of passing in the x of the previous output in order to chain these function calls together and construct this object of the deep neural network in Python code. So what we do is we step through each of these feature map sizes, and this size is used to define the number of feature maps. So here another thing to note is we're using a separable convolution 2D. The separable convolution describes this technique of making it more memory parameter efficient, but I wouldn't worry about that too much for now, and also just using Keras, you can just treat this as a black box. Separable convolution 2Ds, these are more efficient convolutions compared to just the standard layer. But see how this code is looping through this array of different filter map sizes and then passing it in to construct the object by passing in this size hyperparameter. So you loop through 4 times constructing these different layers with the residual connection. Then you take all that output, put it through another convolution, batch norm, activation, and then we do a global average pooling. So average pooling is where you take a neighborhood of 2 by 2 or any kind of neighborhood, and then you take, say, the max value, or in this case, the average value. So it's one way of reducing the spatial resolution of features in a convolutional neural network. And then we append our activation layer. So an activation layer, now at the classes level, this is where we've processed these cats or dogs, and now we're finally making the decision, is this a cat or is this a dog? And this is done by having a feed-forward dense layer that has this number of units. So in this case, it's going to have 1 unit, and it's going to have an activation function, either sigmoid or softmax. So sigmoid is a function that will turn it into either 0 or 1, whereas softmax will normalize the logits into a probability distribution. So softmax and sigmoid, it is worth noting that these are slightly different ways of transferring this output logit into a class label prediction. So then all in all, once we define this model, we return Keras.models. the inputs layer, and then the final outputs layer where we take in this final classification logits and pass it through the activation function. So in this function, we've defined this make model that takes in an input shape of an image and the number of output classes, in this case 2, cat and dog, and then it produces this model architecture. So now we use the keras.utils.plot model to view our model. So as mentioned previously, we begin our model with the input layer, then 2 blocks of convolution, batch norm, and activation. So what this looks like is we have the input, then we have the convolution, batch norm, activation, convolution, batch norm, activation, and now we get to this for loop where we're defining these skip connections. So with the plot model, we get to visualize what these skip connections look like. We take in this previous activation feature maps of 90 by 90 by 64. So this means we have 90 by 90 height by width of this feature plane, and then we have 64 such planes. So this goes into this layer where we pass it through activation, convolution 2D, batch norm, and then 3 of these layers, and then we have this convolution, and then this skips ahead to be added with this feature map. So this is the idea of skip connections. We have this branching in our architecture, and then it skips ahead, and this is a dramatic improvement in information flow that has been one of the biggest breakthroughs in designing deep neural network architectures. So now we've defined our data, we've defined our preprocessing pipeline, and we've defined our model. Now it's time to actually train the model. So first we define the number of epochs. This is the number of times we want the model to step through the training data. So we have training steps, and then we have epochs. A step would define an individual batch of these 32 images, whereas an epoch generally refers to the entire set of cats and dogs, and each time we step through the entire set of cats and dogs compared to just an individual batch. So in Keras, we have these callbacks. Callbacks are an argument you pass to the model.fit function as something for it to do at the end of every epoch. In this case, we're using the keras.callbacks.model checkpoint. So what model checkpoint is going to do is it's going to save our model weights. And this is really important for all these experiments. We're going to want to have a copy of our model before maybe the training is going to collapse, or maybe we want to repurpose this model for transfer learning, or maybe we just want to do some kind of experiments where we want to have a copy of our model weights so that we can load and save our model, pick it up from where it previously was. And this is especially important once we, these state-of-the-art deep neural networks, they're trained for like 2 weeks. So you're training these models for a seriously long time. And an important thing to do that, especially if you're relying on these collab interfaces and cloud runtimes, is make sure you're saving your model weights. That's extremely important. So now we're going to compile the model. We pass in the Atom optimizer with this hyperparameter on the learning rate. We have our binary cross-entropy loss, accuracy metric, and then we pass in model.fit with our trained data set, number of epochs, this callback function, and our validation data. So when you run model.fit, you get to see the current step of the model training, in this case 6 out of 586. This means it's currently on the 7th batch of 32 examples, and it'll have to do 586 batches of 32 in order to step through the entire cat versus dog training dataset that we have on disk. Another cool thing about Keras is it gives us the ETA built into the model.fit. The ETA is the estimated time until it's finished with its entire epoch. In our case, an hour and 15 minutes, which can be incredibly frustrating. 50 epochs is going to take us, 50 hours about. And this is the current loss, this is the current accuracy of the model on the training set. So this is what it's doing on the training set, and then once it finishes the epoch, the Keras callback will tell us how it's doing on the validation data. So in this case, we see that it's taking an hour and 15 minutes to step through the data. And this is because we're currently running on a CPU. So now let's switch this into a GPU and then rerun all this code and see how much faster this is. So now we're running this on one of the GPUs provided by Google Colab. This is much faster compared to the CPU. Look at how it's just speeding through the batches of data. This is a dramatic difference from the runtime that was previously shown when using the CPU. So Google Colab has some really high-powered GPUs. If you're willing to pay, this is the $10 a month subscription GPU, which is, the difference is usually like a Tesla V100 compared to, say, a T4. The T4 is still fast if you're not paying for it, but the Tesla V100, it does have more memory, it is a bit faster, so I personally think it's worth it to pay for Google Colab Pro. But either way, you see this huge speed up compared to these graphics processing units compared to CPUs. This is a very important thing to note throughout all of training deep neural networks. They run much faster on GPUs because you can parallelize the computation on these giant neural networks, which is this forward pass with these big matrix multiplications. So we see as we start the second epoch, we'll get a good look at how long it takes to get through each epoch. So we see we finished the first one, and now what it's doing is it's calling this validation data callback. is going to give us our validation performance. We see in this case we have 62.7% accuracy on the validation set, and we have our accuracy. Then we also had this model checkpoint. So we can go to our folder, and we see here, save at 1. This is what model checkpoint does. At the end of every epoch, it's going to save the model weights. So this is the current frozen weights of our model after it's done 1 epoch of training. So I'm going to stop this training, and we're going to go right into this following code where we're going to run inference on new data. So now that we've trained our model, we want to run inference on new data. We've trained a deep neural network, and now we want to deploy it into the wild to classify a given image and tell us whether it's a cat or a dog. So the first thing to note is that certain layers of our deep neural network are going to be inactive at inference time compared to training time. We use data augmentation and dropout regularization to prevent overfitting with respect to fitting our deep neural network on this data. But during inference time, these layers provide us no utility. So what we're doing in this code is we load this individual image of one cat. We have passing the 180 by 180 image size. We preprocess this image to make it a NumPy array. We use TensorFlow.expand dimensions. This line of code is how you pass one image to the deep neural network, because the deep neural network is used to taking in batches as input size. So you have to use this special syntax in order to reformulate the tensor of an image into a tensor of a batch size dimension. So it's like 0 by 3 by 32 by 32 if it's a CFAR10 image. In our case, 0 by 3 by 180 by 180. You have to expand the dimensionality so that it's compatible with the input to the deep neural network. So now our model is going to run model.predict on this image array. We see our score predictions. This is how much weight the model had put on each of the classes. It thinks this image is 80% cat and 19% dog. So this is how you make predictions with a new image having a trained model. So thanks for watching this first walkthrough of image classification from scratch from Keras Examples. This repository shows you how to load a JPEG image dataset from the disk into the Keras workspace, how to download this dataset from a web link using the curl shell command, unzipping the zip file, and then working with the directory to make sure you have the right dataset, how to get out corrupted images from some bad link or some kind of bad dataset. This is how you basically process these files in Python if that's the situation you find yourself in. So now this is the syntax for loading an image dataset from directory. This is one way of getting data from disk into the workspace for fitting these models. This is how we visualize our images using matplotlib. This was our strategy for applying data augmentation and how you use it using built-in Keras functions, how you visualize some examples of what data augmentation is doing to the data, standardizing the data so it's between 0 and 1, 2 different strategies for basically the key idea is efficiency with respect to the size of your datasets, whether you want to do preprocessing on the CPU or on the GPU. So if you do make it a part of your model, this will happen on the GPU, compared to if you preprocess it and then pass it to the model, where you do this on the CPU. But again, this only really matters if you're doing this at larger scale experiments. So we batch the model, we make our model. This is one way of doing the skip connections and one syntax for learning how to construct a deep convolutional neural network, and then visualizing the model using keras.utils.plotModel. Then we looked at how to train the model, how to define the epochs, callback functions, compile the model, model.fit, and then explaining what happens with the epochs with this little window as we're stepping through the data, and then how to run inference and make a prediction on one individual image after we've trained our model to get a sense of how well it's working.